learning objectives. In this chapter, the user would learn the following in detail: errors under computation, a general error formula, error in series approximation. Errors under computation. When computer programs are being implemented and tested, the errors which can occur include: point number 1, errors in the syntax of the program language, that is, keywords misspelled, operators missing, etc. The compiler will find such errors and present a more or less meaningful error message indicating the problem. Point number 2, errors in coding the program specification or algorithms into the programming language, that is, the program does not do what the user had specified. This type of error is mainly due to inexperience and a lack of understanding of the language. Point number 3, errors in the program specification or algorithms, the set of rules and or formulas and or algebraic steps that the user has specified to solve the problem are incorrect. Example, a mathematician has made a mistake in that the user has specified to solve the problem or incorrect. Example, a mathematician has made a mistake in the development of the equations. It is up to the user to ensure that algorithms being used are correct to the extent required. Number 4, errors due to the storage and processing of numerical data, that is, the accuracy of the hardware used to perform numerical calculations is finite. For example, real number data with fractional components is stored in floating point format with a typical accuracy between 8 and 20 significant decimal figures. Thus, the results of programs using such floating point representation cannot be exact. In addition, many mathematical functions are infinite series which have to be truncated. The set of notes considers the type of error listed in the point number 4 above. Absolute error. The error in the evaluation of an algorithm can be defined to be the true value minus the approximate value as calculated. Usually, in practice, only the approximate value as calculated by the program is known. In general, however, it is possible to determine something about the error without knowing it precisely. For example, using the technique of interval halving to find the root of 4 minus 9x cubed minus 2x square plus 120x minus 130. The iterations could stop at the point when a root was between minus 3.60016 and 3.60013, and it is not necessary to halve and try again. In this case, the maximum error would be 0.000003 and the root was minus 3.600145 plus 0.000015. Thus, although the value of the error is not known, it can be stated that it does not exceed 1.5 into 10 power minus 5. The error is called an absolute error, and one common notation is to write a bar over the symbol to indicate an approximation, to write an E with subscript to stand for the error. Thus, if x is a true value, x equal to x plus ex. Thus, the absolute error is the difference between the true value and the approximation. Addition of measured quantities. If you have measured the values for the quantities x, y and z with uncertainties dx, dy and dz, and your final result r is the sum or difference of these quantities, then the uncertainty dr is r equal to x plus y minus z, delta r equal to delta x plus delta y plus delta z, then delta r equal to square root of delta x square plus delta y square plus delta z square. Here, the upper equation is an approximation that can also serve as an upper bound for the error. Please note that the rule is the same for addition and subtraction of quantities. Example, suppose we have measured the starting position as x1 equal to 9.3 plus 0.2 m and the finishing position as x2 equal to 14.4 plus 0.3 m. Then the displacement is delta x equal to x2 minus x1 equal to 14.4 m minus 9.3 m equal to 5.1 m. And the error in the displacement is 0.2 square plus 0.3 square whole power 1 by 2 m equal to 0.36 m. M stands for meter. Multiplication of measured quantities. In the same way as for sums and differences, we can also state the result for the case of multiplication and division. or equal to x into y divided by z. Delta r by modulus of r approximately equal to delta x divided by modulus of x plus delta y divided by modulus of y plus delta z divided by modulus of z. Then delta r equal to modulus of r into square root of delta x by x whole square plus delta y by y the whole square plus delta z by z the whole square. We obtained these are all from the above definitions and the derivatives. Again, the upper line is an approximation and the lower line is the exact result for independent random uncertainties in the individual variables. And again, please note that for the purpose of error calculation, there is no difference between multiplication and division. Example. We have measured a displacement of x equal to 5.1 plus minus 0.4 m during a time of t equal to 0.4 plus minus 0.1 s. What is the average velocity and the error in the average velocity? Then the displacement is v equal to x divided by t equal to 5.1 m divided by 0.4 s equal to 12.75 meter per second. And the uncertainty in the velocity is delta v equal to modulus of v into delta x by x whole square plus delta t by t whole square whole power 1 by 2 equal to 12.75 meter per second into 0.4 divided by 5.1 whole square plus 0.1 divided by 0.4 whole square whole power 1 by 2 equal to 3.34 meter per second. With the constant. What if you have measured the uncertainty in an observable x and you need to multiply it with a constant that is known exactly? What is the error then? This is easy. Just multiply the error in x with the absolute value of the constant and this will give you the error in r. R equal to c into x. Then delta r equal to modulus of r into delta x. If you compare this to the above rule for the multiplication of two quantities, you see that this is just the special case of that rule for the uncertainty in c, then delta c equal to 0. Example. If an object is released from rest and is in free fall, and if you measure the velocity of this object at some point to be v equal to minus 3.8 plus minus 0.3 meter per second, how long has it been in free fall? Answer. We can calculate the time as g equal to 9.81 meter per second square is assumed to be known exactly. T equal to minus velocity per gram equal to 3.8 meter per second divided by 9.81 meter per second square equal to 0.387 second. The uncertainty in the fall time is then delta t equal to modulus of minus 1 by g into delta v equal to 0.102 second square per meter into 0.3 meter per second equal to 0.03 second. Polynomial functions. What if there is a dependence of the result on the measured quantity x that is not described by simple multiplications or addition? We will state the general answer for r as a general function of one or more variables below. But we'll first cover the special case that r is a polynomial function of one variable x. R equal to x power n. Then delta r equal to modulus of n into delta x by modulus of x into modulus of r. You see that this rule is quite simple and holds for positive or negative numbers n, which can even be non-integers. General functions. And finally, we can express the uncertainty in r for general functions of one or more observables. If r is a function of x and y written as r of x comma y, then the uncertainty in r is obtained by taking the partial derivatives of r with respect to each variable, multiplication with the uncertainty in that variable and addition of these individual terms in quadrature, r equal to r of x comma y etc. Then delta r equal to square root of dou r by dou x into delta x whole square plus dou r by dou y into delta y whole square plus etc. All rules that we have stated above are actually special cases of this last rule. We leave the proof of this statement as one of those famous exercises for the reader. Errors in series approximation. Assume that we are given a series and we ask a computer to sum up its first zillion terms. We get the total 1000. What we are to think of this number? Is the series divergent? Say to infinity, but slowly, so we only got to 1000, but eventually we would get arbitrarily much. Or is it convergent? If yes, how close to its sum is that 1000? Obviously, such questions cannot be answered. There are some tricks, but none of them really reliable. We know that we sum up a series by investigating the sequence of its partial sums, so it is very relevant. In fact, the key example there uses series. In order to get at least some answers, we have to restrict ourselves to convergent series. We start by formulating the question we will want to answer. Consider a convergent series, summation k equal to n naught to infinity ak. For n greater than n naught, define summation k equal to n naught to n ak. If we replace the sum of the series by this partial sum, what is the error? That is, we define the remainder, or n equal to summation k equal to n naught to infinity ak minus summation k equal to n naught to n ak equal to summation k equal to n plus 1 to infinity ak. Fact, consider a convergent series, summation k equal to n naught to infinity ak, let n greater than n naught. Assume that g is a non-increasing function such that modulus of ak less than or equal to g of k for all k greater than n. Then or n less than or equal to integration n to infinity f of x dx. Consider a convergent series, summation minus the whole power k bk, where bk greater than 0 and bk forms a decreasing sequence tending to 0. Then we have modulus of Rn less than or equal to bn plus 1. Conclusion. In this chapter, we have covered the following in detail: errors under computation, a general error formula, error in series approximation,